Thank you. Alrighty, I'm so excited to be here. Thank you. And today, of course, we'll be talking about Nerves and open source hardware. Before we get started, quick show of hands. Who's used Nerves before? Okay, a pretty good amount of you. For those of you who haven't used Nerves, how many have used or have a Raspberry Pi maybe lying in a drawer somewhere? Okay, good. Awesome. So before I get started, a little bit about me. So my name is Gus. I'm from the US. I currently live in Luxembourg. My background is in computer engineering. I operate really at the intersection of hardware and software. After moving to Luxembourg, I founded Protolux Electronics, a small consultancy to provide custom hardware, software support. I specialize in Nerves, but also microcontrollers and other things. I've been working with Elixir for 7-ish years, and I love it. I love the Nerves framework. It's just great. So I'm really excited to be here. This is my first ElixirConf. A brief overview of what I'm going to talk about. So first off, there's a few people in here, it seems like, that maybe haven't used Nerves before. I'll give a high-level overview of that. And then we're going to switch and talk about the hardware product development lifecycle. I'll introduce what Trellis is, the project timeline, and how you can use it in your products. So first of all, Nerves framework. At a high level, it's the way that you can run Elixir on hardware for embedded devices. It specializes, is really great in IoT, industrial devices, but is really used across industries. I know of companies using it in like autonomous boats, smart energy infrastructure, lighting control systems. There's a whole bunch of really cool projects out there that use Nerves. At the core of Nerves is a series of, let's call them scripts, that are part of your mix compile process that create a minimal custom Linux tailored to running Elixir. So when your device powers on, it immediately boots into your supervision tree and starts booting up your Elixir applications. It also is an ecosystem of libraries to interact with hardware and that Linux subsystem. So this includes hardware peripheral and communication protocols, like there's GPIO support, UART, I2C, all these sorts of things. But there's also other parts of the ecosystem which are really nice. Like time and clock management is surprisingly difficult on embedded devices, and Nerves does a great job of making that easy for you. Another big one is the firmware update experience. I think Nerves has best-in-class support for firmware updates on devices. A little bit of a view of where does Nerves run. So once you have a Nerves system and a Nerves application, where can you run it? It can run on any Linux-capable device, but the popular and officially supported ones by the community include like Raspberry Pi. Most people know this one. BeagleBone Black is a more industrial-focused type of single-board computer. And then GRISP2 here, this board is a project coming out of the running Erlang on embedded devices. I think Pierre is somewhere here in the audience. Yes. So also runs Elixir with Nerves. So there's and RISC. GRISP. Yes. So there's a lot of really cool hardware that you can run on. And we heard earlier today about like Nerves is focused on Linux-capable devices, but we heard earlier today about how can you run on microcontrollers and really resource-constrained stuff with Atom VM. Again, these are different projects targeting different things, so I just wanted to make that clear again, that we're targeting high-level Linux. So switching gears into like, what does hardware product development look like? Now, some people, when I say product development, and since this is ElixirConf, you're thinking like software products. But when you're talking about hardware products, they usually have 3 components. It's not just software. We're talking, there's usually mechanics, there's a design, there's an enclosure of your physical product. You have software, which of course is the algorithms, the control of the devices, and then the electronics. Electronics is interesting because it's the glue between your software and your mechanical and your design. It's what glues together the control of your device and the actual inputs, outputs. Maybe there's motors, buttons, things like that. So you can't talk about a hardware product without considering all three of these things. Now, I've shown here on the screen Google Nest, the Nest thermostat. It was a product released, I don't know, 10 years ago at this point. But it's a smart, intelligent thermostat for your home. I hope most people are familiar with it, but I'm going to walk through what does it look like if we wanted to make a Nerves-enabled smart thermostat. So to begin this product development process, we might start with what's called breadboarding, where you have jumper wires and you're connecting things externally. So for this type of testing, you would have an off-the-shelf computing platform like Raspberry Pi. You connect external sensors, external actuators, and you connect them with these jumper wires. They can be like this with a breadboard, or it can be soldered, but it's generally the same idea. The difficulty of getting started with something like this is relatively low. You can buy all the parts off the shelf. It's relatively flexible in how you connect things, but it has several downsides. It's pretty bad for a couple of things. It's not very portable. You wouldn't want to strap this to your wall and say, hey, here's my smart thermostat. That's not exactly the most user-friendly experience. It's also hard to reproduce. So someone had to do the effort of connecting each of these wires individually. And I mean, that's very error-prone. So these are not great for products, but it's great for testing because you can try things. The next level is like a hat. HAT stands for like hardware attached on top, a phrase coined by the Raspberry Pi community. It's where you still use an off-the-shelf computing platform, but maybe you add a custom circuit board on top. This one here is one that I built. It is it adds extra hardware, all your sensors, interfaces, into a very reproducible and more portable type of design. So it improves the reliability, it improves your reproducibility, because you can have these manufactured in a factory and sent to you. And a lot of companies might stop here. You can build a product with Raspberry Pi as the computing platform, and it's good enough. It works. However, it still has some downsides for the user experience. You are still constrained on the form factor of your product by the Raspberry Pi. Additionally, like there's other Raspberry Pi versions called like the compute module, which is smaller. It doesn't include as much of the connectors and peripherals, but those still cost quite a bit. And at least for Raspberry Pi, which is one of the most popular platforms, they're traditionally like really, the chip on the Raspberry Pi is really good at displays and video. It might not be necessarily so good in other products like automotive and industrial. And then finally, this type of hardware design still has a lot of waste. For example, a product which has no display in it has no reason to include an HDMI connector. However, if you're shipping with a Raspberry Pi, it has an HDMI connector. That HDMI connector is essentially just e-waste, and it adds cost to your BOM. So this brings us to stage 3, the full custom hardware design. And if we're looking at the Nest again, you can see from the teardown here that it is a pretty complex process. There's multiple circuit boards involved, batteries, but one thing that you'll note is that it minimizes waste. It minimizes cost. They didn't put a single extra component on there that wasn't absolutely necessary to make the product that they need. But at the same time, they have maximum flexibility. It enables designs which might not otherwise be possible from a form factor, from a number of perspectives. Now, of course, the difficulty is quite high, but the flexibility is high. Let's look at this board. It's also part of the Nest. They have the freedom to place the mounting holes where it makes most sense, to put the connectors in the most optimal location. that can optimize the thermals of this chip. So again, full custom hardware is really powerful. But developing custom hardware is hard. It's called hardware for a reason, and that's because it ain't easy. So what if we could instead have the flexibility of custom hardware, but reduce the difficulty to that more on the level of the hat approach? So this is where Trellis is to be used. The goal is to make developing custom hardware for Nerves easier. And so what Trellis is it's open source hardware. Now, this is actually not so clear as like open source software. A lot of companies might say that their hardware is open source, but only release a schematic so that you know how things are connected. When I say open source hardware, I mean open source hardware. Everything is open. The schematic is open source. The layout of the PCB is open source. The source files will be completely available, and they're designed in a free and open source software called KiCad, so really accessible. It also have a permissive license for use in commercial products, and it comes in 2 variants. So the first is like a core design. The core design is the bare minimum that you need to get code running on a processor. Everything else is bring your own. That is great because I can do the hard part of implementing the difficult parts, whether it's the high-speed interfaces for interacting with your storage or things like that. And then you can bring all of your peripherals that make your product, right? The second variant of it is the development board. This is an example of how you would use the core design in a product, per se. We'll see more about this in a second. But going back to like Trellis itself, it is Nerves first hardware. And because it is designed for Nerves, it can have the best experience integrating with other tools in the ecosystem. For example, there's the ATEC 608A crypto chip on board, which allows you to connect to Nerves Hub, the really awesome Nerves firmware update tool. If you haven't used it, check it out. It's really great. But having this chip on there means that we have deep integration and can ship a production capable board for Nerves Hub. And additionally, there will be a maintained Nerve system for the development board, so you can either get started or you can use that as the base for what you want to build next. The name is one thing that I want to clarify because maybe not everyone has a background in gardening. But Trellis is like an ornate fence or support structure placed to allow certain types of flowers or plants to climb up it. And so I named it Trellis because I want Trellis to be a platform for you to grow on, a platform for you to grow your product, to grow and just build on. Now, if you open up the repository for Trellis, what will you see? So there's, 2 main parts that I had hinted at before, but you have a schematic, which is basically just the wiring diagram that shows you how all these chips are connected together, things like that. It's just a symbolic representation of your circuit board. That's what you see here on the left. Then there's the layout, which is how the PCB is actually connected, where the copper is etched away is the layout. Now, Trellis includes both, and I've tried to do my best to add as many comments as possible so that it is easy to follow, easy to understand, easy to adapt. But having the pre-done layout means that you can take the pieces that I've done already, which are more difficult. High-speed signaling routing can be tricky sometimes, but if you have the proven design, then it makes it easier. For the development board, you can see here kind of what it looks like. It has a Raspberry Pi form factor. It has a compatible 40-pin header, so technically you could use any existing hat for Raspberry Pi, bring in the software support, and use it in your application. However, the development board is different from Raspberry Pi in a number of ways. One is that you can see there's the USB, the full USB ports plus Ethernet connector I've traded that out for more industrial interfaces, because that's one of the things that this chip really excels at. So there's a CAN connector. CAN is like used in automotive. If you wanted to hook this board up to your car and read air codes or things like that, that's something you could do. There's RS-45, another differential signaling protocol, which is used in like robotics and often in like satellites and things. There's Wi-Fi on there. So it's an example of how you could integrate a Wi-Fi chip, a microphone to show some of the analog capabilities. There's a quick connector, which is just I2C, standardized I2C connector, which allows you to plug into like third-party boards with no soldering, which is really great. And there's a wide like 16-volt DC input. So diving in a little bit more, I mentioned the CPU is really good at industrial things. But if you're looking at the specs, it is decidedly mediocre. It's dual core, 1.2 gigahertz. It has 256 megabytes of DDR3 RAM inside the chip. It's like, it's not a lot, to be honest, but it is really good for a couple reasons for this type of application. The first of all is that the RAM being in the chip means that there's minimal external parts. That's less that can go wrong in your designs and easier to bring up. It's also quite easy to work with and like get a hold of. There's generally wide availability. You can have it assembled at a factory for your own custom boards pretty easily. And the third thing is that it's really cheap. We're talking like the chip itself for the CPU is around $8 in single-digit quantities, but that drops to like 6 when you're buying more than 100 or so. So additionally, the package is really nice. It's easy to solder. Well, easier to solder. Maybe not easy. And then it has a lot of supported peripherals, as I mentioned, especially on the industrial interfaces. So a quick comparison. Should you between Raspberry Pi and Trellis. Now, Raspberry Pi, as mentioned, has a lot more computing power, but it maybe lacks in a few other areas. It's not open source. You can't customize it to your liking, which again constrains your form factor for your products. It maybe doesn't have as many peripherals as some of these other chips. The cost is going to be higher, but there's an asterisk there, because again, you'd have to be buying maybe quite a few of these boards before that becomes true. But there's one big one where Raspberry Pi wins out, and that is availability. There are 5 of these boards in existence. Here's one of them. I forgot to hold this up earlier. But the availability is a big one, right? So when you're looking at this chart, should you use a Raspberry Pi? The answer is probably. But it's useful to know that there's tools like this, Trellis, in the ecosystem where once you get to the point where you need custom hardware to make the user experience that you want for your product, there's a solution for that, right? Trellis might not be a good fit for every project, but if you're doing industrial hardware interfaces, or you need flexibility in form factor, lower cost, or you just want to support open source hardware and Nerves first hardware, then maybe this is something you should take a look at. So let's take a look at the timeline of where we are. So this project started earlier this year in January. It's been kind of the side project or part-time work for myself and a bunch of people who have been helping out with it. But the hardware development is pretty much done, as you can see, because I have the boards here. But we're in the process of bringing up Nerves on it, getting software support, getting everything ready so that it can work just like the other Nerve systems. That means that once that's up, I'll have this release open publicly, and then eventually I'd like to produce a batch of dev boards to make this available to the community, because again, this project is for the community and I want to get people actually using it. The big thing here is that I think the project is, I want to get it in the hands of people, and if there's companies or individuals interested in this, I'd love to hear from you guys about how you would plan to use something like this so that we can make a better product, make a better dev board and experience. So that's pretty much all I have here, but I did want to give a huge special thank you to a number of people who have helped with this. Frank, over here, yes, has helped out a lot with getting Nerves brought up, and Chris Dutton, who's not here, has helped financially. He helped buy some of the first batches of boards, as well as doing some design reviews for the hardware. Lars has been a big supporter from day one, and my lovely fiance Clara has been helping behind the scenes. So again, if there's anyone that wants to be or is interested in using this type of hardware, let's get in touch. I'm on Blue Sky. I post a lot about the board and the development process. Also on Elixir Slack, Elixir forum. I pretty much use this profile picture everywhere. So awesome. Thank you.
Thank you so much. I see we have one question. We have time for exactly one.
I posted this on the app as well. What's the low power story?
The low power story. So Trellis is not, I haven't designed it to be like extraordinarily low power. Does it support low power mode? I'll have to wait and see once the software development, how low it can go. If you're familiar with some of my other projects, I have one called Soleil, which is a hat it's the one I showed earlier. It's a hat on top of Raspberry Pi, which basically cuts the power off until later. It would technically be compatible, and maybe one day I'll do a mashup of the two where you can get a low power mode on Trellis. But to be determined.